can use the results that we obtained last time uh, to develop really an approximation, which is the plane wave approximation to spherical waves, and that's the content of this segment. If you remember, we had actually done this um, and had developed the following relation for really a general wave and a general medium, three-dimensional. I think last time we used a Y here, thinking of it as a water wave, and an amplitude factor here. But our interest is light, and light, as we'll see, is a is a wave phenomena, or at least can be viewed as a wave phenomena in certain situations, and uh, and ultimately, everything arises. All sources of light arise from essentially point light sources. It arises from quantum mechanical transitions, primarily in atoms. That in the transition they emit light in the form of electromagnetic radiation, really. And we'll say more about that shortly. But so because it's we're looking now at light, I'm going to start using E, really a general form for any wave, but in particular we're going to focus on E, the electric field component of the electromagnetic wave. Um, I, I'll try to use script E. Maybe a few times I will lapse into to a block E, but for the electric field, because remember I'm using primarily the block E for energy. If you remember, we because of the 1 over r squared fall off of the intensity and the fact that the intensity of light is proportional to the amplitude squared, we get that the electric field in our case falls off as 1 over r with distance. And that really comes out of the 1 over r squared fall off of light intensity with distance as an experimental fact. The alpha is to account for absorptive media or lossy media. And then we have either a sine or a cosine for these radial spherical waves. The spherical waves, k r minus omega t, plus possibly a phase shift. A lot of times I'll just set that equal to 0. And then we've got something here that I'm going to start calling E, not bar. It's a constant with a bar over it. It's not really the amplitude per se, as we'll see. It's the spherical amplitude in a certain sense, but a constant. So at least in terms of the electromagnetic theory of for light waves, this E naught is a constant, it's a spherical amplitude. Alpha is the absorption constant for the medium, for if we have lossy medium. K is the usual wave number. Omega is the angular frequency. F is the regular frequency. We'll also use the auxiliary formula that the velocity of the wave is equal to omega over k, so we can get that from here. And then delta naught is a phase shift if needed. And again, as I've said, these I could easily have used a cosine function here. They're sort of interchangeable in these harmonic waves. And symbolically, I can represent this function up here. I kind of think of this in terms of a water wave, in which I've got something that's moving the water up and down at this point with a strong amplitude, and then as it goes out radially, its amplitude drops off, primarily from two factors. One is this 1 over r dependence, and the other is this exponential damping. If I go out to any other point, a distance r from it, well, that point at that point oscillates up and down as well. I think of this as water, for instance. Then I'd have a cork here that just bobs up and down, and a cork here that simply bobs up and down, but with lesser amplitude. The amplitude generally decreases here as you go out. Uh, from peak to peak, we still use the convention from peak to peak as a full wavelength, even though the amplitude is decreasing. So any two peaks for these waves. Uh, if you look at this, if this were a water wave on the top of a lake, and I look down on the lake, what I would see is the point source, and expanding about this, moving outward, are these circular wave peaks, in which I've got this peak here would be this. I'm drawing these circular lines for the wave fronts, okay? And the distance between these would be the distance. Well, this would be the 1, 2, 3. So 1, 2, 3. This distance here would be a wavelength, and that corresponds to these two wave fronts here. So point source expands out really in spheres about it, uh, and they move outward with the velocity. It's the wave velocity. In the case of light in a vacuum, the velocity that these things move outward, then move outward from the central source. So they're moving out in this direction, this direction, this direction. The spheres are expanding with a radius that um, is ever increasing, um, and moving outward with a velocity that's the speed of light in whatever media this happens to be, or if it's a water wave, it could be the velocity in the water of the water wave. Well, uh, it turns out that for the transparent media, like we're going to be considering primarily in optics, and that's things like the vacuum, air, which is close to the vacuum, glass of various sorts, the transparent, clear plastics, etc. Um, the absorption constants, alpha, they are very, very small for all of those. And so we don't make it, it's not that it's zero, and if you went through maybe thousands of kilometers of regular glass, you would see some absorption and some loss due to this exponential damping factor. But uh, uh, over the scales that people usually consider optics, uh, distance scales and light transmitting over that, then we can take the alpha to be equal to 0. And that gives us that this exponential factor in our general expression just becomes 1, and so we're reduced to this. This is really what's generally referred to as a spherical wavelet. It's undamped, so there's no loss in the medium. It's an approximation. Really, even for the best vacuums that we can produce, presumably there is some materials in otherwise empty space. Between galaxies, for instance, there's a very, very low density, but there's probably particles and electrons and protons for sure. And as a result, there can be a very small damping factor, even for propagation through what we would generally call the vacuum or intergalactic or interstellar space. And so, and there you go over very, very large distances. And so, even though alpha may be small, for large distances r, this factor is not necessarily equal to 1. But for laboratory scale optics, this this E is just this constant. Again, kind of a spherical amplitude times this factor. Again, the sine could be a cosine function. Oh, I said that there. Yeah. These are generally called scalar. This would be a scalar wave. This might be like a sound wave, where here E might be the pressure, and P naught would be a baseline pressure related. But for us, either the sine or the cosine version, I'll refer to those as spherical wavelets, and we'll leave the realm of any absorptive media throughout the rest of this course anyway. Well, the really any wave from a point source in really any kind of media. This could be a point source of sound, and it'd be sound waves up here, or of these general wavelet forms. And now then, what I'd like to do is take a look at that in a slightly bigger perspective. So I have a point source over here, and it expands about it spherically. So all of these are parts of spheres. Of course, I can't draw all of the spheres here. But eventually, as I get further and further away, these spheres have such a large radius that over at least the scale that we would measure things, these spherical surfaces that are for us all separated by a wavelength. Remember, we're looking at the peaks here, so the distance between any two of these is a wavelength, so they should all be equally spaced in a wavelength. And if I go a distance very, very far from it, so in this region over here, that's a distance, a fixed distance r naught from the source, then if r naught is much, much greater than lambda, I can make the following approximations. And that, in fact, is to not put our coordinate system here, but to translate it over to here about some point that's a distance r naught away. And then I can measure the distance r to some point from this coordinate system is just the distance x. And pretty obviously, r naught plus x has to add up to be r. Again, we're looking at peaks. For light, the lambda is very small, right? 500 or so nanometers. Yeah? But let's look at cosine. I could have used sine here as well. So now I replace the r by r naught plus x. And then collect terms a little differently. K times x, k times r naught I put over here, minus k times r naught, k times x, minus omega t, and then I group these. These are all constants. K is a constant, r naught's a constant, and that fixed translation to the new coordinate system. And then r is just r naught plus x. And then I factor out the r naught. And now then I look at the case where r naught is much, much bigger than x. I'm observing these waves passing by over a distance x. Remember, x is from our coordinate system here, in which they all essentially look like straight line, nice planar type waves. And at that regime, I can factor out the r naught, so x over r naught is very small. In fact, the distance r naught is much, much bigger than x, as I said. Typically, x is on the order of maybe a few wavelengths, and r naught is on the order of maybe a few centimeters or meters. And in any event, I'll approximate x over r naught as small, and so this denominator becomes approximately 1. And so now it's an approximation, but it becomes E naught over R naught times this cosine, and I can consolidate all of these into a single phase shift and consolidate these two constants into a single constant, which is now really the true amplitude of this plane wave, this sinusoidal or harmonic wave. So for large distances from sources that have very short wavelengths, actually, we get the plane wave approximation. Again, it's approximation, but it's a very, very good one. For light, lambda is 500 nanometers, which is something like that. And so this lambda over r naught, and if x is maybe even many multiples of this, then it still is a very, very small number, about 1 part in 20 million. And so I can take out a few million wavelengths here to get to reasonable distances. Plane wave approximation. We'll use it almost exclusively.